Let's see if I think they can still get all that. Back it up a little bit. All right, hopefully everybody's seeing me in the video, and let me get back here. Okay, how are you guys today? How are you doing? Can you hear me? Can you hear me? Can you hear me? Okay, okay, good, good. If you can turn your cameras on, turn your cameras on, so I can see your face. I can play so much better when I can see you. Stand up, stand up. You need to stand up. Let's stand up. Let's stretch. Let's stretch. Oh, it's Friday. It's Friday. Let's sit back down. Let's sit back down. It is going, I mean, I swear, the next 7 days are going to be like the best week of the year as far as weather. I mean, like, it's going to be like one of those stunning weather days. Stunning. If you want to know something fun to do, it's just a blast. And it'll take probably, well, I got two things, but something that is just a blast. If you've got a bunch of, if you have a Skyline Drive pass, there's something called Bear Fence Rock Scramble. Bear Fence Rock Scramble. It's about a 1 mile. It's about a 1 mile loop. It's about a 1 mile loop. But the views that you get, and it only takes like about 40 minutes to get there from here. Okay, so you go up on Skyline Drive into Elkton, get on there, and then you head north. You head north about 7 miles. That is a fun 4 hours. I mean, there are just moments where you're sure you're going to die. There are just moments where you're just like scrambling these rocks and you're like, ooh. I had when my kids were young, I took them on it. And like, I was like, holy hell, like they could die. I mean, if they step off, I'm like, and one kid's just has no fear. Like, oh, look at this, I'm gonna climb to the edge of this. And I'm like terrified of heights. And I'm like, no, you're not going anywhere, get back here. You know, but when you get up there and you get this 360, and it's only cost you like half a mile, you're like, whoa. So yeah, that is a great day, okay? Especially on like when that bright sun and it's in the 50s or 60s, that should be an incredible time. Bear Fence Rock Scramble. Another thing, before you leave JMU, you should go to Reddish Knob. Before you leave JMU, you should go to Reddish Knob. Again, okay, you can drive up there. As long as there's not a lot of trees on the road. Okay, so, okay. All right. What was not on Quest 1? What was not on Quest 1?
The cross product?
The cross product. We have our 3 vector products. Was the scalar product on there? Was the scalar product on there? Was the dot product on there? Okay, so all these products run there. All those products run there. But our cross product wasn't. Okay, here's our definition of the cross product. We have two vectors. A cross B is the result of a dot product of two vectors a scalar or a vector? Is the result of a dot product of two vectors a scalar or a vector? A scalar. Is the result of a scalar times a vector a scalar or a vector? A vector. Okay, the cross product two vectors is a vector. And to be a vector, if you're in V, if you're making a proof, if you're in V, then you're a
Ordered triple.
An ordered triple of 3 real numbers. Okay, so it's a vector, so it's going to be an ordered triple of 3 real numbers. What are those 3 real numbers? Write them down. If you fill that in. What are those 3 real numbers in terms of the components of A and the components of B? Without looking at your nose, whatever you got in your brain. I just want whatever you got in your brain. Because quest 2 will be here before we know it. Quest 2 will be here before we know it. And you know it's going to just focus a lot on cross products. Okay, what do you guys have? What do you have? What's the first component? What's the first component of the cross product vector?
A2, B3 minus A3, B2.
Very good, very good. It doesn't have the ones. It doesn't have the ones. You're in the first component and it doesn't have the ones. It's A2, B3, you go up, minus A3, B2, you go down. What's the third component? What's the third component?
A1, B2 minus A2, B1.
A1, B2 minus A2, B1. Similarly, it does not have the third. Similarly, it doesn't have the third components. And you go up, A1, B2 minus A2, B1. Then there's the more complicated, but not that much more complicated, third component. I mean, middle component, second component, not the third component, the second component. It's not going to have any of the A or B subs. It's not going to have any of the A or B sub 2s. Because it's in the middle, it's the middle child, okay? It's the middle child, it has middle child syndrome, okay? And so it's A3B1 minus A1B3. Now to test you, to see if you guys have this, I have two vectors on the board. My B vector is 2, -1, 3. My B vector is 2, -1, 3. And my A vector is 1, 2, 1. My A vector is 1, 2, 1. B, 2, -1, 3. A is 1, 2, 1. And what I want you guys to do is calculate the cross product of those two vectors. Calculate the cross product of those two vectors. And while you're working, go to grid view. Turn your Zoom to grid view. Also, guys, I understand from my daughter, JMU just gave you access to Zoom. That you guys should all have access to your own Zoom account through JMU. So you should be able to have unlimited long Zoom meetings. So just letting you know that that's available. Okay, wherever you're at, stop and just hold it up so all of us can see. Let me see what you guys have. Let me see what you've got for your, now I get to see what you guys get to see. I'm seeing let's see here, I think Rhett's I can see the best. I'm seeing a 7, -1, -5. David, I'm seeing a 7, -1, -5. I'm believing the chances of two people doing it wrong the same way isn't good. So I believe the answer is 7, -1, -5. How many of you, raise your hands. How many people got that? Raise your hands. Wave to each other. Okay, so now what I want you to do, I guess, is make me number 1 again. Make me number 1. Dr. Warren's number 1. Now what I want you to do is go into your Canvas, go into announcements, and open that plotting routine announcement. Have we done plotting in this class? I don't know. Have we done plotting of vectors in this class before? Have we done that? No. Okay.
No.
So go to the announcement. Okay, where it's like I forget what I called it, 3D plotter or easy 3D plotter. This is something from the National Science Foundation. This was something from the National Science Foundation. And what I want you to do is go open that up. Go open that up. Okay, I know you, sorry guys. I'm still going to use the microphone on this camera, even though I'm over there. So it's going to sound like I'm in a railroad tunnel trying to talk to you. Let me know if you can't understand me, okay? I'm afraid to change the mic, that'll never get it back. Okay, can you hear me?
Yes.
Okay, I'm going to share my screen. Can you guys see this? Can you see this?
Yes.
Okay. Now have your window that has the same thing in it open. Do you see the little X there? Do you see the little X beside the function that's showing on yours? Push that X and say go away. Make it go away. Click the X and make it go away. Okay, the next thing I want you to do, I know it's hard because I just have one window, you have two. Do you see this select, this drop-down menu? Click on that drop-down menu. All right, the only thing we're going to be concerned about is this thing called vector. So click on the thing called vector. Click on the thing called vector. And I'll do the same thing. Now, what you see should be something like what I have here. This is where you would put in your three numbers for your vector. Don't do that yet. Don't do that yet. This is where you get to pick a color. And so why would they pick black? I have no idea why they would make that. So what I want you to do is I want you to enter, kind of like what I did down here. My A vector was 1, 2, 1. I want you to enter that in for you. The but will be at 0, 0, 0. Remember, vectors are vectors anywhere in three-dimensional space. And make that a red vector. Make that a red vector. So you guys go ahead and do that. How many people have a red vector? How many people have a red vector? How many people have a red vector on theirs? Okay, is the but at 0, 0, 0? Is the but at 0, 0, 0? Okay, I want you to add another vector. I want you to add another vector whose but is also at 0, 0, 0. But make that the B vector, and B is going to stand for blue. So make it a blue vector. So your A is red and your B is blue. And while you all may be attention deficit like Dr. Warren, you're also multitaskers extraordinaire. Put in a third vector that's your cross product vector and make that green. Put in a third vector that's your cross product vector and make that green. So you should have 3 vectors when it's all said and done. Okay, I'm just going to move to the front here. I shared my screen again, just so you can hear me. How many people have three vectors? How many people have three vectors? How many people have a green vector, a red vector, and a blue vector? Okay, now look at the screen I shared. Look at the screen I shared, and look at where that hand is. Look at where that hand is by that 3D mode, and just click on that. Okay, and then what I want you to do is I'm going to move to the front. Go back and look at my window. Go back and look at my window. And I'm going to yell because I'm up the front of the room. Let's change these. Let's change these. These are just defining your box. Let's change these to like maybe -6. So the maximum x is -6. Sorry, the maximum x is 6. The minimum x is -6. And do that for all three of these. Just change all of them from 2s to 6s. Once you're done on yours, hit the graph button. Once you're done on yours, hit the graph button. Okay, now go back to my window. Go back to my window. Go back to my window. Now the nice thing about this plotting routine is you can grab parts of it and spin it around. And that's what's fun, because it gives you far better sense of what's going on in three-dimensional space. So go ahead and do that. Go ahead back to your window and do that. Play around with that. Just drag and hold it, move it around so you get a sense of how that feels. Now come back to my window. Sorry, I know this is miserable, but come back to my window. Now I'm going to move this around. What do you notice about the green vector and the plane that contains the red and blue vector? I think about the plane that contains the red and blue vector. What do you notice about that green vector? And maybe you can see it almost right there the best.
It's below this, it's below the XY plane.
It's below the XY plane, we've got that, but as far as like the plane that contains the red and blue vector, Gordon, if I'm looking at that,
Perpendicular.
it's perpendicular. That the cross product vector is perpendicular to both A and B. Okay, now I'm going to stop sharing. Make me number one. Does that help? Does it help seeing vectors? Does it help seeing vectors in three-dimensional space? A little bit. So you guys can play with that. You can plot these. I'm going to give you assignments on that, and you're going to take screenshots of what you have, okay, and turn them in at some point in time. Because you need to visualize what's going on. I mean, think about it. Think about how impossible this is. We've got things moving in anywhere, any angle in three-dimensional space, and we're working with it geometrically with this new algebra. It's so freaking cool. It's just so cool. So say this. The cross product vector. Hands on the
Vector
is perpendicular
is perpendicular
to both A and B.
and is to both A and B.
So the cross product vector A cross B is perpendicular to both A and B. Well, that would mean then that A dot A cross B should be what? If this vector is perpendicular, if those two vectors are perpendicular, then that dot product should be what? That dot product should be what? This should be 0. It should be 0. Have at it. Have at it. Try to prove that. You're now going to prove essentially that A cross B is perpendicular to A. So you try to prove that. I don't need a formal proof. You just try to prove it. Use your definition of your vector cross product and your vector dot product. You're combining both of them. And try to justify that they're perpendicular vectors. Don't worry about me, I'm talking to my video people. There are a lot of you that weren't in class today in both my first section and my second section. There was a lot of you that weren't in class, okay? Okay, you better be watching my video. You better be watching my video. And I want you plotting those vectors too and doing everything I'm telling everybody else to do. Okay, wherever you're at, stop. Wherever you're at, stop. And look up at the board. Okay, wherever you're at, stop. And let's see where we're going. How many people are pretty comfortable? How many people are pretty comfortable with replacing A with its component form? How many people are pretty comfortable with that? How many people are pretty comfortable that this second expression, A2B3 minus A3B2, and so on, is the cross product? How many people are pretty comfortable with that? Is the dot product of two vectors a scalar or a vector? Is the dot product of two vectors a scalar or a vector? Scalar. So this is going to be a scalar. Using the definition of the dot product, it's this component times that component. First component times first component. Second component times second component. Third component times third component. And that's how I'm getting to this line here. And I'm going to read it And you can check if you got the same thing. You should have A1 times parentheses A2B3 minus A3B2 plus A2 times parentheses A3B1 minus A1B3. Then plus, now our third components, A3 times A1B2 minus A2B1. How many people got to there? How many people were at least heading that direction? Now it's just real numbers. Now it's just real numbers. I distribute like you would, like really any sixth grader. The subscripts they'd be terrified, but there's nothing hard here. We're just distributing A1 times A2 times B3 minus A1 times A3 times B2 plus A2 times A3 times B1 minus A2 times A1 times B3 plus, now distributing the last one, A3 times A1 times B2 minus A3 times A2 times B1. Now, for any one of the 6 terms that's positive, that doesn't have the minus, circle one of them. Circle one of the 6 terms. It's a magic trick. Circle any one of the 6 terms that has the positive. And I'll do the same thing. I'm going to be really lazy, and I'm going to pick the first one. Now, what I want you to do is find the brother that's the minus, the exact same term, but it's the minus. Okay, this is just kind of like a psychology test. How many people picked this one like I did? How many people, raise your hands, how many people, you just picked the very first one? You just picked the very first one. I don't know what that says about us, but I don't know what it says about everybody else. Maybe the other people are more creative. I don't know, maybe they have more creativity. If you picked this one, then this was the guy that would kill it. This is the guy that would kill it. How many people found the guy that would kill your guy? How many people found the guy in this video game that would kill your guy? Okay, so what happens is all 6 of these terms cancel out, and we're left with the number what? All 6 of these terms cancel out, and we're left with the number what?
0.
We're left with the number 0. We're left with the number 0. Now, guys, if I had made this a B and not an A, if I'd made this a B and not an A, the same thing would happen. You can go through and show that the exact same thing will happen. Okay, so now I've got this beautiful, well, maybe not so beautiful. I made it, okay. Can you guys see it at all? Can you guys see this? Okay, so this is the vector A, this is the vector B. This is the vector A, and this is the vector B. And what I'm going to do is I'm going to look at the cross product vector. I'm going to look at the cross product. I'm looking at the cross product B cross A. Does B cross A point towards you? Or does it point towards the floor? Does it point more up or does it point more down? Does B cross A, because we've got to think in 3-dimensional space. Does B cross A point more up or down? Take your karate chop, put your hand on the B, and you swing it towards the A, and the right hand rule, that thumb points up. A cross B, I'd come underneath, whoop, I'd come underneath and go that way, and the thumb goes down. Now, it's a little hard for you to see. I'm going to move this green vector, and you tell me when you think it's actually the cross product vector.
There.
Yeah, I mean, it's a little hard to see with this wide angle lens, but this vector should sit perpendicular to the plane, that contains A and B. Should sit perpendicular to the plane that contains A and B. It's too fun. Could you prove it? Could you prove it that the cross product sits perpendicular to both A and B? Could you prove that? Could you justify that? Math is.
Proof.
Prove. Okay, guys, look at me, look at me, look at me, okay? They're for most of your careers, okay, all of the stuff I teach you in Calc 1, Calc 2, and Calc 3, you're not going to use on a day-to-day basis. I'm not kidding myself. I'm not fooling myself. Think about your parents. They may be in a technical field. They're not doing the cross product very often. Right? But the concept of proof, validated, justified arguments, is something that will serve you every day of your life. If you look at every single problem that's set in front of you as a mathematical proof, where you've got to put together logic and justify every single step, you will be better at whatever you do. And the only place to learn that is in mathematics. The only place to really learn it and be trained in it is in mathematics. So the most important thing I can force you to do is proofs. So guess what you have to do for homework? Guess what you have for homework? Proofs. Okay, so let me talk about your proofs. Let me talk about your proofs before I do my proof. Okay, your proofs are this. I want you guys to prove that the cross product is anti-commutative. It's our first product that's not commutative. That B cross A doesn't equal A cross B. B cross A doesn't equal A cross B. And the right-hand rule shows it. Whoop, up, whoop, down. But mathematically, I want you to show that the vector B cross A is equal to -1 or negative A cross B. So that's one of your homework proofs. The second one is over here at this part of the board. The second one is over here at this part of the board. Now I'm going to see if you can read it. This helps me know how big I'm writing. Read this to me.
Alpha times A cross B.
The vector alpha times the scalar alpha times the vector A cross B
Equals
A, that's the vector A, cross
alpha B.
the parentheses alpha B. A cross parentheses alpha B. So those are two proofs you're supposed to make for homework, as well as doing the homework in 12.4, as well as doing the homework, the cross product homework, which should be becoming easier, Okay. Stand up. You're going to want to stand up. Our second quest will be here in a heartbeat. And you will be making proofs. You'll be making proofs. Stretch, grab your magic lasso. And Alexander, Cameron, and Brandon, your arms better be flying through the air. Okay? And you guys at home on the video, throw your magic lasso. If you are watching this video and you're not throwing your magic lasso, oh no. Wrap up your attention span. And sit back down. I'm going to make the hardest proof. Are you okay with that? If I take the hardest proof. Is that okay? Can I do that? Okay, so we already are a little frustrated because some stuff that we always took for true in the real numbers isn't true with vectors in this product. A dot B equals B dot A. We can prove that. But A cross B doesn't equal B cross A. Another thing I've got to ask, does A dot B plus C equal A dot C plus B dot plus A dot C? Can you distribute the dot product? Yeah, it's incredibly useful. And I've got to ask the same thing, is the cross product distributed? We're calling it a product, but can I distribute my cross product around vector addition? I know you're tired, but you just wrapped up your attention span. A vector plus a vector is a
Vector.
vector. Can you visualize it geometrically? If you have a vector A and you have a vector B with the head-tail rule, can you visualize the sum of two vectors? So this is a legitimate vector, B plus C, in the parentheses. I'm going to cross it with A. What will the result be, a scalar or a vector? What will the result be, a scalar or a vector? A vector. A vector cross a vector is a vector. Okay, I'm going to prove that in fact the cross product's distributive. You can distribute A across B plus C. That this is equal to A cross B, that vector, plus A cross C, that vector. Okay. It's going to take most of the rest of the period to do this. It's going to take most of the rest of the period to do this. So let's get ready. I'm going to prove number 4. I'm going to prove number 4. And I'm going to start up here. I'm cleverly going to write the word. What did I just write? What did I just write? Prove. Okay. Anytime we start a proof, we're given crap. Anytime we start a proof, we're given crap. Okay, this is what we're given. This is one of the things we're given. So on a test, that would be written for you. On a test, this would be written for you. Given A, B, and C are elements of the vector space. Given A, B, and C are elements of the vector space. And what I want to do is I want to go from here, to there. That side's equal to that side. This side, typically the left side's given to you, and you want to reach the right side. Okay, imagine that you're going to play a soccer game, and you've just driven up to the stadium. What's the first thing you got to do? You're going to play a soccer game, your team's there, and you're just driven up to the stadium. What's the first thing you have to do?
Get out of the bus.
Yeah, get out of the bus. Get off the bus. And that's the first thing we got to do here. We got to get off the bus, get everybody on the field, listen to the Star Spangled Banner, okay? And then we start the game. And that's kind of like the same thing here. We've got to get all of these guys out of the bus. So this is the way the proof would start. Given vector A, vector B, and vector C are in V. Then, what's that word I just wrote? What's that word I just wrote? Not the then. What's the word I just wrote beside it?
There exists.
There exists. You go to China and you write this down, and whatever is in Mandarin for there exists, anybody who's in mathematics will know that that's what that means. There exists, well, I mean, like, what does it mean to be in V? Well, you're an order triple of 3 real numbers. So let's get our real numbers in play. Then there exists a real number A1, A2, and I'm just going to keep writing and not talking. And I'll let you copy them down. There exists A1, A2, A3, B1, B2, B3, C1, C2, C3 that are all elements of the
Real numbers.
real numbers. Then this notation is not as accepted in China. This is not as accepted. S dot T dot means such that. It's our laziness for such that. Such that the vector A is equal to the order triple A1, A2, A3. The vector B is equal to the order triple B1, B2, B3. And the vector C's equal to the order triple C1, C2, C3. Now, the most important thing I can teach you is proofs. Okay, this is the logic. Now we provide the justification. What's allowing me to so boldly say these real numbers must exist and these ordered triples must exist? What's allowing me to say that? What would be your justification next on the next quest? What would be your justification?
Definition of a vector.
By the definition of our vector space. By the definition of V. By the definition of our vector space. Okay. Oh, say, can you see? Okay, we now have the Star Spangled Banner. Now we're ready to start the soccer game. Let's get everybody. One person's going to flip a coin. Somebody's going to start with the ball. I don't know if they flip a coin in soccer. Sorry, I watch football. I know soccer's the future. I get it, but I still don't quite get it. I know there's a midfielder, okay, and I know there's a striker, which always sounded like a lot of fun. Okay, that seemed to be the fun position. I never quite got goalie. I never quite understood that position very much, but it was probably the one position I could play since I can't run. Okay, so now the Star Spangled Banner's in play. Let's get everybody on the field. Okay, so we would then, given the left side, given A cross B plus C, given A cross B plus C. Now this is going to be equal to, now guys, I'm going to make 2 steps in one. I'm going to make 2 steps in one. What did I just say?
You're gonna make 2 steps.
I'm going to write down the justifications, and you're going to write down the logic. Dr. Warren, you said you were going to do the proof. I know, I lied. Okay, my justifications is by substitution. By substitution, I'm using vector substitution, but you can just say substitution, since everything else will be properties of the reals when we're dealing with the real numbers. And my vector addition, and my definition of vector addition. I'm doing vector substitution, and I'm doing vector addition. Now you're like, Dr. Warren, what are you going to substitute? I'm like, are you kidding me? Do you not see what you just wrote down? Do you just not see what you just wrote down? So I want you to use vector addition and vector substitution to write down what you think we could get away with our next line of logic being, knowing we want to end up over here, knowing we want to end up on the right side.
Hey, Dr. Warren, what's the vector substitution? What does that look like?
It's just SUB, sorry, sub, and then there's parentheses S.
Okay, thank you.
And again, that's a Dr. Warren laziness. I can't spell substitution, so whenever I can't spell a word, let's just abbreviate it. DEFN. THN. Remember orders of operations. You work inside the parentheses first. This is active learning. Well, for some of you don't look so active, but this is active learning versus passive learning. Eventually, I'm gonna have to be like Captain Scully and land in the Hudson, land this plane in the Hudson. What we're gonna do right now is wherever you're at, stop. Okay, I know this is active. Now you're gonna be passive learners. Okay. If I'm making a substitution, what can I substitute for the vector A? If I'm making a substitution, what can I substitute for the vector A?
A1, A2, A3.
Yeah, this ordered triple. So let's do that. So we would have A1, the ordered triple, A1, A2, A3, okay? And that's just my substitution. Now I'm gonna still have my cross product, but now I'm doing my vector addition. I'm adding the two vectors. I'm adding the two vectors inside the parentheses. We start inside the parentheses first. I could substitute this ordered triple for B, and I could substitute this ordered triple for, I'll see if you guys actually can see me on the screen. I'm going to substitute this ordered triple for
B,
B, and I'm going to substitute this ordered triple for
C,
C. And then I'm going to add those two vectors together with your definition. You guys define vector addition. What would the first component, the first real number be in my vector addition? What would it be?
B1 plus C.
B1 plus C1.
B1 plus C1, this is the way we add vectors, then B2 plus C2, then B3 plus C3. How many people feel like they could have gotten to there? How many people like if you're making this next, I don't know when our next quest will be. Probably not next Wednesday, but the next Wednesday. Probably not next Wednesday, but the next Wednesday. Okay? But if you were doing that, how many people think they could get everybody off the bus and at least get to this far? At least get this far in the game. Okay, now you're not going to like the next justification. You're not going to like the next justification. My next justification in my proof is that. You're like, no, Dr. Warren, you just wrote that above. No, that's different. That's not vector addition, that's vector what? That's vector what? That's not vector addition, that's vector what? Cross product. Yep. You've got the cross product of two vectors. Have at it. You know how to cross, you know the definition of the cross product. I wish I had you guys 8 hours a day, Monday through Friday. We could have so much fun together. But you gotta stop wherever you're at. I just wanna make sure we get this. The cross product. We started class with this. If you have a vector cross a vector, it's the second component of the first vector times the third component of the second vector. And then the rest of that. So I look here. I've got A1, A2, A3. So I take the second component of my first vector, and multiply it times my third component, b3 plus c3, of my second vector. And so that gives me my a2b3 plus c3. Then we have the minus. And that's right here. Then a3 times b2, which would be my second component, which is b2 plus c2. And then we keep doing the same thing for the other components. Now, if you didn't finish, just write down what I read off. Just write down what I read off. In the second component, it should be the scalar a3, the real number a3, parentheses times b1 plus c1. Then the minus a1 times parentheses b3 plus c3. And that's my second component. A3 times b1 plus c1 minus a1 times b3 plus c3. My last component, a1 times the second component in my second vector, b2 plus c2. a1 times parentheses b2 plus c2 minus a2 times parentheses b1 plus c1. Now I don't know how many hands I'm going to see in the air. Did anybody get that far? Did anybody get that? Is there anybody who got that? All right, the next step I'm hoping any 7th grader could do. Next step I'm hoping, now suddenly we're in the real numbers. What I want you to do is distribute all of those things out. And I'm going to have to erase part of my proof. I just erased something that I wanted. Okay, again, I gotta stop you, being Captain Scully here. I've gotta stop you. Hopefully you guys have this. If not, I'm making a video, you can go back and look. If I distribute the first one, I'm gonna get an A2B3 plus an A2C3. Then I'm gonna distribute here, and I'm gonna get a minus A3B2 minus A3C2. Now, if you forgot to distribute this minus, you're in Calc 3. You should get yourself a stick and non-whip your hand. Just non-whip your hand. Because you got to stop that. You're engineers. You're chemists. You should non-whip your hand to make sure that doesn't happen. We haven't been non-whipped. I'm filming this. Sorry. Maybe I shouldn't use non-whipped. Okay? We haven't been non-whipped enough to stop ourselves from doing stupid things like that. Okay, the next component in my vector is A3B1 plus A3C1. Now we don't want to get non-whipped. Minus A1B3, then minus A1C3. And then similarly, the third one would be A1B2 plus A1C2 minus A2B1 minus A2 times C1. No, I really think you guys should be making your cross-product flashcards. You should be making your cross-product flashcards. I really think somebody who had their flashcards down could probably unpack the bus, get to there, do the notice orders of operations, start in the parentheses first, do the vector cross-product. If you're like me, ADD, you're probably going to screw up a sign somewhere or screw up something else. But somebody who's like detailed, I really think could get at this point. And this is where you kind of have to take the helicopter out of Vietnam and you kind of like, okay, what are we doing? What are we trying to show again? I've completely forgotten. Where are we at? And we're like, okay, we're trying to show the distributive property. We're trying to show the vector A cross the vector B plus C distributes. It equals A cross B, that vector, plus A cross C. Okay, over here, what would be my justification on the line that we just had? I left it off. What have we done? What have we done? What can you get away with because it's COVID? What can you get away with because it's COVID?
Algebra of the real.
By algebra of the reals. Anytime you're using just moving components around in any way, it's algebra of the reals. Okay, now I'm going to be Captain Scully and I'm going to land this plane. I'm going to get the A's and the B's together in each term and the A's and the C's together. I'm going to get the A's and the B's together in each term and the A's and the C's together. So I've got my vector. I've got my three components in my vector. And what I'm going to do is I'm going to get the A's and the B's together and the A's and the C's together. I have A2B3 minus A3B2. I'll even put parentheses around this. Plus A2C3 minus A3C2. Getting the A's and the B's and the A's and the C's together. And similarly in the other components, I'm going to do the same thing.
Dr. Ron, would you mind saying what you write a little bit
Sure,
slower so we can
sure.
see?
Sure, Nick. A3B1 minus A1B3, then plus A3C1 minus A1C3. And then in my last component, A1B2 minus A2B1 plus A1C2 minus A2C1. Oops. And this is again just the commutative property and associative property, just the commutative property and the associative property of the real numbers. Now I've got to land this plane. We're almost done. My next justification is going to be vector addition. My next justification is going to be vector addition. I'm going to break this single vector into the sum of two vectors. I'm going to break this single vector in the sum of two vectors. And so my next justification would be I'll have a vector plus a vector. I'll have a vector plus a vector. My first component is going to be all the A's and B's. My first vector is going to be my A's and B's. My second vector is going to have my A's and C's. So I would have A2B3 minus A3B2. Then I'd come and grab this guy, A3B1 minus A1B3. Oh gosh. Then I grab this guy, A1B2 minus A2B1. And similarly, I do the same thing. I do the same thing for my C's. And again, you guys can watch the video. You can watch the video. It's a lot clearer in the video. Well, not a lot clearer, but at least a little clearer. I similarly grab the C's and the A's. A2C3 minus A3C2. That's the first component. The second component is going to be the A3C1 minus A1C3. And then I'm gonna have my final component, the A1C2 minus A2C1. And if you wanna look smart to your parents, just show them this proof. They'll be looking at all this and be like, this is impossible. This is impossible. You understand this, son? You understand this, daughter? You understand this? You're like, kind of. Okay, let's finish the proof with this. By vector cross product, let's land this in the Hudson. My justification is going to be vector cross product and my vector substitution. I'm going to do my vector cross product and my vector substitution. I've got a vector that's A2B3 minus A3B2, A3B1 minus A1B3, A1B2 minus A2B1. Was that on the board anywhere else today? That's your vector cross product. Substituting it in, back in the bold form versus the component form, that's A plus B. But I come over here, I've got A2C3 minus A3C2, A3C1 minus A1C3, A1C2 minus A2C1. What's that?
A cross C.
Perfect, Gordon. A cross C. Does the vector cross product distribute?
Yes.
It's not obvious why. We use it all the time. Physics, you just assume it. You just do it. You don't prove it like we did. The proofs I ask you to do for homework are a lot shorter. Okay, you're going to leave now, but I mean, how many people kind of understood what we were doing? I mean, how many people played the game with me and were you missed some shots, I'm sure. But you're learning to play. Okay, you guys have a safe weekend. Listen, it's going to be so beautiful. It's going to be such a beautiful weekend. This is going to be one of the most beautiful weekends of the entire year. It's going to be so beautiful. Get out and enjoy. Embrace the weather. Even in COVID. Do not breathe on each other. I need to have you back with me. I need to have you in the classroom. October 5th. I'm believing. I'm kind of believing. After spring break, after fall break. Okay, I will see you guys. Be safe. Thanks for playing. Yes.
Just like on, I think it was Monday's class ends at 11.
Oh, crap. And you're right. I almost made the same mistake. People left. I was like, yes, thank you, Caitlin. I feel so much better now. Yay, stand up. Everybody else is like, Caitlin, if we could throw stuff at you right now, we would. Stand up, David. You need to stand up. I can't believe I did that. Yes, just like on, I don't know how I get this. Thank you. Bless you. I'm like, where does the time go in my second class? I'm such a train wreck. Okay, sit back down. Okay, let's have some fun. Imagine that I've got two vectors. Like this, sitting anywhere in three-dimensional space. I've got a vector A and I've got a vector B. Okay, and I want to talk about the perpendicular projection. No, you don't want to. No, you won't know, Dr. Warren. I want to talk about the perpendicular projection of the red vector onto the blue vector, of A onto B. I want to kind of justify why we call it the perpendicular projection. And so it was a little hard before, but I think it'll be a little bit easier to see here. Maybe I'll go like that. Imagine that I've got a vector sitting here. This is my red vector, and I'd like to talk about the perpendicular projection of this vector, which is coming out at me, onto my blue vector. So I'm not sure how much of this will translate. I'm hoping you would. So I've got my light. I've got a flashlight here. Oh, sorry. Okay, I got a flashlight. I just blinded myself. Okay, so I'm here, and what I want to do is I want to cast a shadow, which will be the perpendicular projection, but I've got to go at it, I've got to go directly above it. Can you guys see that shadow on the blue vector? Is that reading at all? Let me move it around a little bit. So if I move it around, can you see the shadow move? If I go right where I'm at 90 degrees, that shadow vector is a parallel. That's what you were calculating. And then if I come off it at 90 degrees, that would be a perpendicular. That would be a perpendicular. But the reason we call it the projection vector is because of the light. It's the shadow. We're projecting the red vector onto my blue vector. Okay, so I don't know. To me, that's so much fun. Were you asked to find a parallel and a perpendicular? Were you asked to calculate that?
Yes.
Yeah. Now, how freaking cool is it that you can do it? You're like, well, what do you mean, Dr. Moore? Well, imagine like you've got any two vectors in three-dimensional space just sitting there, somewhere in three-dimensional space. And I'm saying, oh, give me a vector that's parallel to the green vector, perpendicular to the green vector, and makes up the blue vector. You're like, that's black magic, man. You can't do stuff like that. Oh, yeah, you can. And you can even plot them on the graphing routine that I just showed you, that plotting. You can actually put the tails in that thing wherever you want and see it. It's so cool. The power I'm giving to you, you should use for good, not evil. Do not become calc bandits. Become calc heroes. Don't steal like on Wall Street. Sorry, okay, back to where I'm here. This next one's so fun. We're going to start with something called Lagrange's identity. So write down the word Lagrange. This is Lagrange's identity. It says this. The norm of A cross B squared. Now I gotta ask, how many people can calculate the cross product now? How many people feel like they can calculate a cross product of two vectors? How many people know how to take the norm of two vectors? How many people can take the norm of two vectors? Okay, so we're just taking the cross product, getting a vector, and taking the norm, squaring each of the components, adding them together, and looking at the square root. The squaring's nice because it gets rid of that. Is equal to the norm of A squared, the norm of the first vector squared, times the norm of the second vector squared, minus, and you're like, whoa, okay, minus A dot B squared. And this is Lagrange. This is Lagrange's identity. Now, the interesting thing is Lagrange lived a little bit after Euler. Well before vectors. So even though this is Lagrange's identity, it was never written in vector form by Lagrange. He wrote it in component form. He had it all in component form. Gibbs wrote it like this. And Hamilton wrote it like this. Okay, now, for sake of time, what's the definition of A dot B? Dr. White, I can't focus. You can do this. What's the definition of A dot B?
A1, B1.
A1, B1?
Plus A2.
Plus A2, B2 plus A3, B2. How many people have that? How many people have that down? Okay, now, using the law of cosines, not the definition, using the law of cosines, what else is A dot B equal to? Norm of A, norm of B, cosine theta, where theta is the angle between the two vectors. So I'm looking at that. I want to replace A dot B with that identity that this is equal to the norm of A times the norm of B times the cosine of theta. So you guys go ahead and do that. Take that, write an equal, and what I want you to do is replace that A dot B with the norm of A times the norm of B times the cosine of theta. Now I even went another step further. I squared everybody. I put it in there and I squared everybody. I just took it a step further. How many people are following so far? How many people have this so far? How many people are with me? Or how many people are in the bobsled? Are you guys with me? Okay, so all we've done is use the identity we derived from the law of cosines. Now what I notice is that there's a norm of A squared, norm of B squared, but over here there's another norm of A squared and another norm of B squared. Factor that out. Factor that norm of A squared and the norm of B squared out of those two terms. Factor the norm of A squared, norm of B squared out of those two terms. And what you're left with is 1 minus cosine squared. You're left with the norm of A squared times the norm of B squared times 1 minus cosine squared. But my little math geniuses, 1 minus cosine squared is sine squared. Now notice how sweet this is. We've got this squared is equal to this squared, this squared, this squared. Take the square root of both sides. Take the square root of both sides. And we get this beautiful identity for the norm of the cross product. We get this beautiful identity for the norm of the cross product that I swear, you could never really get using components. If you took A cross B and squared each of the components, added them together, if you could see that this was equal to the norm of A times the norm of B times. Now guys, I know most of you, probably 95% of you, forgot the absolute value. It is not true always that the square root of x squared is x. If x is positive, yes. If x is negative, no. So there's actually an absolute value there. Okay. Caitlin, you're a saint. Thank you so much for saving the class. Okay, guys, we'll talk about the geometry associated with this beautiful identity on Monday. We'll talk about the geometry associated with this beautiful identity on Monday. Bear fence, rock scramble, bear fence, rock scramble, bear fence, rock scramble. Did I talk about that, right? Bear fence, rock scramble, bear fence, rock scramble. Okay, I will see you guys safely on Monday. Have a good weekend. Thanks, guys.
The first three properties and the alpha A cross B proof.
Yeah, Cameron, yeah. You go after those. It'll be great to set you up for a quest 2.
All right, thank you. Have a good weekend.
You too, Cameron. You too.
Bye.
Oh, you just stopped my video. See, I just wish it looked this clear to you guys. I wish it looked this clear to you. I mean, this is my Zoom. This is the way it looks like to me on Zoom, but somehow it doesn't look so clear to you guys. I know it doesn't.